if the group number is not written, I'll just not consider it. It takes, I mean, sorting 500 sheets, almost 450 sheets, it takes time. Okay, so we have these numbers over here, and then I need to worry about what is the, so remember that curve that, so Gibbs free energy, I hope I labeled everything. Yeah, the Gibbs free energy of the product minus the Gibbs free energy of the reactant is what I wish to calculate, and see whether it's a spontaneous reaction or not. So let's see who can do this fast. Haha. It's there in my notes. So delta G naught reaction comes out to be, huh? Why did I write 28.6? We'll take it 28.6, so because I have the numbers for that, huh? Huh? Okay. Okay, forget it. Maybe I typed something wrongly. Anyways, but I'll use this, even if it's 30.8, just to tell you what, and otherwise I'll have to use a calculator and work out everything. Okay. So take the real value, whatever it is. Now, Kp. If I know the delta G of reaction was equal to minus RT log Kp. So that is Kp is equal to minus delta G by RT, e to the power of this number. So e to the power minus, now this is kilojoules, so 28600 joules per mole. It's not a bad idea to write the units. Divide by R, joule per Kelvin per mole, divide by temperature was 298, what we have taken, and that comes out to be e to the power minus 11.54, which comes out to be 9.7 into 10 to the power minus 6. Okay, which is a very small number, right? Which means the reaction hardly occurs. If I mix hydrogen and carbon dioxide, this reaction hardly occurs. Yes? If I've asked you to calculate how much of it has converted, right? So what is the value of X? Yes? So how much of carbon monoxide has been formed for that matter? Then you would say that, okay, my Kp is very, very small, right? That's the value of Kp, right? And if it's very, very small, then I can assume that the extent of reaction is very small. So the value of X is very, very small. So, you know, that Kp is nothing but the pressures of the products divided by the pressures of reactants at the equilibrium value. So the pressure of products was X square, need some more space, X square, and the pressure of reactants was A minus X, B minus X. And if I say, okay, that X is very, very small, so it's very small with respect to A or B, then I can as well write this as X square by AB, right? And for that matter, I just took one value, that A is equal to 1 mole and B is equal to 2 mole, and since X is very much less, so 1 minus X is approximately 1, 2 minus X is approximately 2, that is X square by AB, and which gives X approximately 0.0044
mole.
Right? So if you want, you could solve it exactly. This is also possible, right? You have only one variable, one equation, so you can solve it.
The other example that I have taken over here illustrates another principle. So we'll just go over that one. And that example is N2O4 in equilibrium with 2 moles of NO2, also in the gaseous phase. Okay, so initial number of moles, I have N, here I have 0. At equilibrium I have N minus X, here I have 2X. Oops, sorry. Then the mole fractions would be, the total would be N plus X, right? Yeah. So N minus X by N plus X and 2X by N plus X. So this is initial, that's at equilibrium, that's the mole fraction at equilibrium, right? Okay, so then I have to worry about Kp. Kp is nothing but products by reactants. So partial pressure of NO2 squared, now we have to worry about the stoichiometry, divided by partial pressure of N2O4. So Kp would be equal to, right, the partial pressure of NO2 squared by partial pressure of N2O4, which would also be equal to the total pressure square X of NO2 square divided by the total pressure. So I just write 1 times pressure over there, X N2O4, and that I know is equal to pressure into 2x over n plus x divided by n minus x over n plus x. Oh, there's a square, sorry. So I'll have one more n plus x over here, and that would be a square. So which is equal to p times 4x square, n square minus x square, and if I write the extent of reaction as alpha is equal to x over n, then what I get is p times 4 alpha square 1 minus alpha square. Okay. So the amount of reaction that occurs, if I rearrange these things, then the fraction reacted alpha comes out to be 1 plus, I'm not calculating, I'm just seeing and writing this, Kp to the power minus 1 by 2.
Okay, so you could do a calculation of it. Take all these things on the other side. This is Kp, right? I didn't write that. Okay. So then you get alpha is equal to 1 plus 4p by Kp to the power minus half.
Now, you see an important principle out here.
If pressure increases,